In this one, we're going to go through the first of GAMSAT Section 3 crash course kind of videos that I wanted to do. A lot of people said in the comments that they'd really like to see one. So we're going to do our best to run through all of it. It may take quite a few videos. Today, we're going to start with physics, and we're just going to be going through the basics of scalars and vectors, and then as well as that going through the concepts of forces and gravity and how they relate. What I will say is the first thing is that this content, even though it's all the underlying principles of GAMSAT, they're not going to directly assess them all the time. Sometimes they do, but it's not going to be the same as like a standard science exam. I think you already know that. So this series is going to be designed to give people a foundational understanding of the content itself. It's still going to be in a GAMSAT context, so where I can, I'm going to try and make note of how they actually assess this knowledge or some different ways to think of things rather than just rote learning formulas. Because in reality, the majority of the formulas that we even go through are going to be given in the questions, but there are some simpler ones as well that are good to have handy to kind of help your way through them. So this is going to be going from the ground up. So for people who have no science knowledge whatsoever, or people who are coming from a non-science background in particular, can really make use of this. But even if you've done a science degree, I know I'm targeting physics because a lot of people who have science degrees haven't studied physics, or they haven't studied in a while and they're not so confident in it. It'll be working its way up further and further as we build, and you keep kind of following along and watching them. You'll get a stronger understanding of it, which means they'll probably start to move faster and faster as we kind of build on the existing knowledge. I'll also try to touch on chemistry and biology in some other ones, and the goal will be to have all three of those areas being targeted as we go through the content. But I think at the moment, particularly physics is the kind of broad issue for most people. Chemistry will come in second, and then biology will start to layer in third. That seems to be kind of the strongest area for most applicants. And even for people coming from a non-science background, is probably the most accessible of the three, but we'll still go through all that as well. The other thing is this is not like an exhaustive list of everything that can be assessed. There is no formal syllabus for the test. This is just based on what I've seen as being the most frequently used and things that would be the most helpful for problem solving, and that's really what we're going to focus on. You can still go and Google some of these things, learn a little bit more about them, but this is not designed to be a set of videos that then teaches you how to do the theory and therefore you can ace the GAMSAT or anything like that. It's to give you the skills so that you can reason with it confidently to go through then the problem solving kinds of questions that they give you in the real test. All right, so let's start here. I've put down just a list of the things that we're going to go through. So you can see scalars and vectors, adding vectors in 2 dimensions. Newton's laws we'll go through as well, gravity and gravitational fields, then looking at normal forces and apparent weights, driving forces and frictional forces, and then finally net force and equilibrium, which is where GAMSAT's really most applied. But we won't be able to get to that until we go through the theory itself. So let's start with scalars and vectors. This is the very first thing we need to kind of wrap our head around in physics. So the idea is that these are looking at different quantities. So scalar quantities are quantities or values that only have a magnitude, right? So magnitude only. And vectors, they have a magnitude, but they also have a direction at the same time, and we have to be mindful of that. So, and direction. So some examples of these, technically you can argue time has a direction, but we can treat time as a scalar. So time is one of them, measured in seconds, and we'll look at something called SI units as well, which are your standard units of measurement. I'll keep kind of noting those as we go through them. Some other ones though that we come across are mass in kilograms. And then we also have, let's see, some other things like distance, measured in meters. And we'll also have speed as well, which is measured in meters per second. These are some of the common ones. We won't be dealing so much with these two or really time today all that much. We will be dealing with mass though as we go through. With vectors, they have both a magnitude or a size and a direction. So this can be things like, for example, weight, which is actually just a measure of force, right? So this is measured in newtons, just like any other forces, which will obviously be predominantly focused on. There's also then things like displacement, which we'll get to in another video, I think. And that's also measured in meters, but it's kind of like the vector equivalent of distance. So just to explain the difference here, if we think about distance, distance is just how far you've moved, right, in any particular direction. So if I had my house here and then I was to walk and then go out here and then return back home, technically I've moved some distance. Let's say that's like 3 kilometers. But my displacement is my straight line distance from my starting point and my ending point. So technically, because I started here and I ended here, then it means that my displacement is actually 0. So my displacement is 0, but my distance is 3 kilometers. And so I can't really put a direction to my distance because I've kind of moved in all kinds of different directions. And the idea is distance doesn't actually have a direction to it. It only has a size or a magnitude. My displacement though, in this case, I can't put a direction to it because it has 0. But say I actually ended over here instead. So I've walked all the way along here and then ended here. Now I have some straight line distance between my start and my end point, and that might be something like 0.8 kilometers. And that has a direction to it as well. It looks to be, if we take a compass and say that that is north, and it's looking to be just slightly northeast overall. And we could put a bearing to it and all the rest of it. I won't go into that because that's really not what GAMSAT's focused on. But we can see that some quantities have directions to them and others don't require directions at all. So as well as that, the equivalent of speed in vector quantities is going to be velocity. So it works very, very, very similarly, but again, it's measured in meters per second, same units, but that is looking at the change in displacement or the change in position, sorry, over the change in time. And so your change in position is your displacement, which has a direction. So as soon as you have a vector quantity in your calculation, then you're going to be calculating a vector as well. And there we go. So all we really need to take from this is to understand that vectors have a direction to them, and we have to be mindful of that when we're working with them. So then the next thing is adding vectors in, or working with vectors in 2 dimensions. So vectors in 2D. So let's say, for example, I was to start here at point A, and then I was to walk south by 10 meters. And then from there, I was going to then walk 15 meters like that and to the east. And I'm going to land here, and let's call this point B and then this point C like that. If I wanted to talk about my displacement, for example, then that would be the straight line distance from my start point to my end point. This would be my displacement. And so in order to actually work out what that is, I need to break down my movement into a vertical component and a horizontal component, or in this case, a north-south component and an east-west component. And this one's pretty simple, right? We can use a bit of trigonometry here, and we could use Pythagoras' theorem. So the square of the 2 short sides are equal to, or add up to, the square of the longest side, the hypotenuse. So 10 squared plus 15 squared should be equal to c squared, and we can just solve for c. So this would be 100, this would be 225 c squared, and this is straight into the maths at this point. 325 is equal to c squared, and then c would equal the square root of 325, like that. We won't worry about the decimals here in this case. So this is one example of it, right? You'd use trigonometry to work out the bearing from north, like this, and work out some angle and then describe the direction to it as well. What's more important is looking at what happens when you add vectors together. So say we had one vector going like this and then another vector going like this, and they're kind of angled up and towards each other in this particular case. What you have to do is break them down into their horizontal component and then their vertical component, like that. So you can see we're always making right angle triangles, and they should always go end to end like this. And so the same thing, I'll do a different color here though. I can do this and this, and those two would refer to the orange line pointing up. So it's got a left component and an upward component overall. And so if I want to add these 2 orange lines together, let's call them A and B, like that, then all I have to do is add up my horizontal components and add up my vertical components. So my horizontal components, you can see, are pushing at each other and are equal to each other, right? So let's say we give them values. I'm making them up here for simplicity, but let's say this one has a value of 10, and so does this one over here. And then over here, this one has a value of say 8, and again, let's just make this one 8 as well. So because the purple and the green horizontal lines are equal but opposite, they're going to cancel each other out. And a good idea is to create what's called a positive and a negative direction. So if I put a key on my diagram here, I can just say that logically, positive should be this way and negative should be that way for horizontal, and positive should be up and negative should be down for vertical. So really, this green one here is actually a negative number. And so when I'm adding them, I'm actually just doing 10 plus negative 10, which is 10 minus 10. And that gives me then 0. So they're going to cancel out. What's going to happen with the verticals though from these orange vectors is they're going to add up because they're both moving in the same direction, right? So 8 plus 8, they're both in the positive direction. So 8 plus 8 gives me 16. And what that means is that the net vector, whether this is force or velocity or anything, is going to be upwards, and it's going to be quite a bit larger. It's going to have a value of 16 now. So I can predict that, say this was 2 tennis balls of equal weight, moving at equal velocity and acceleration and everything else, and I'm trying to work out what direction are they going to move in. Theoretically, they should crash into each other and move vertically upwards, right? With a slightly faster vertical speed than before, like that. And there we go, and that's all you have to do to work in vectors. You can do the same thing. We haven't quite gotten to forces just yet, but we could do something like, let's say there was like a box and there was a rope attached here and then a rope attached here. And someone was pulling in this direction and someone was pulling in that direction. And we want to know which way does the box move. Let's say this one's pulling with a force of 100 and this one's pulling with a force of 50, like that. Then we can work out, we can make a right angle triangle, has a downward component and a leftward component. This one has a rightward component and an upward component to make those right angle triangles, like that. And so then we could work out, let's say we have angles as well, they'd have to give you that. Let's say this is 20 degrees and this one here is going to be 20 degrees as well. It's obviously not to scale. Then I know that this here would be 70 degrees, the leftovers of 90, and I've got my triangle, and I can work out, I'll call this X and Y, and I'll call this W and Z, like that. And I could go through the trigonometry to work out each of their horizontal and vertical components, right? Again, I'll probably leave that for a maths video specifically, but W in this particular case would be 50, and then sine 20, and then this one over here, Z would be 50 cosine 20, and so on, blah, 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 blah. And then let's say that we get, I'll do a different color so it's a bit clearer. Let's say here we get like 40 and here we get 30. May not be right, so we can check the maths, but, and then over here, we might get something like 80 and then 60, like that. And so what that really means is all you have to do is look at the box and go, okay, well, it's got horizontally, it's got a force pulling this way with 40 and a force pulling that way with 80, right? And then upwards, there's a force of 60 and downwards, there's a force of 30. So if I work all of those out and again, put my negatives in, this is a negative, this is a negative, and I add up all my parts, then let's do the vertical first, 60 and then plus a negative 30 is a positive 30, so positive goes up. And then negative 40 plus 80 is positive 80 going that, positive 40 going that way. And now I've got my two parts. I always want my arrows to go end to end. So I'm actually going to move this one just over to here. And then I can see that the net direction of the box is going to be in that direction. So I know the box is going to move somewhere like that, right? Now, you'd only do that in an actual full-on calculation question, but this is just to prove that everything with vectors, even if it's at angles, all you need to do is think about it in horizontal and vertical components, and you can break the whole thing down. When you look at it like that, then you're just adding and subtracting, pulling and pushing. All right, so moving along then, what did I say? I've already forgotten. Newton's laws, here we go. This is where things get interesting. I might move over to here, just to here. All right, cool. So Newton's laws. So we use these a lot in the GAMSAT. So the first of them is just that it's the law of inertia. And I mean, you don't even need, like, the high school thing is like to go through the whole definition of it, right? I'm not going to bother with the definitions of it, but the basics of it are that it suggests that any object should remain in the position it's in or remain at the velocity that it's trying to move at unless otherwise acted upon. So in order to change the movement, that includes something sitting stationary, of an object, you need to apply some unbalanced force to it from outside. It won't do it on its own. It's relying on a force to be applied to it. So this is like the classics of the tablecloth trick of, you know, pull the tablecloth and all of the dinnerware stays on there. The idea is that they all have an element of inertia. They're all trying to stay in place whilst an unbalanced force attempts to move them. The difference is, so long as the tablecloth is like silken or something, then you have no friction and therefore no force applied, even though the tablecloth is moving, and so they should try to remain in place overall. If something catches it or something like that, then the force is applied, and then it tries to resist it and it tries to stay where it is and gets overbalanced as the force pulls from underneath like that, and then everything goes flying. It's the same idea as, like, particularly for anyone from Melbourne who's watching, if you get on a tram or you try to tram surf or anything like that, when the tram kind of rocks around, your body's trying to stay in place. And so when you feel it accelerate or something like that, you pull back, it's because your body's trying to stay where it is while the tram's trying to move in front of you, right? You're not actually falling back in a sense. The world around you is moving forward. The second one is then probably the one that we use the most. So this is the concept that a net force is equal to the mass of an object multiplied by its acceleration. And we can interpret this in two different ways. You can think of it as the force required to accelerate some object of some mass to an acceleration. So say we had, for example, a little car like this, and it has a mass of 1,000 kilos, and we want to accelerate it to 3 meters per square second, right? The force that that's going to take, at least the net force applied to the car, let's say we were pushing from this side, is we would need to push with a force of 1,000, so mass 1,000 times by acceleration. So we'd need to apply 3,000 newtons of force in order to accelerate it at 3 meters per square second. If we keep applying that 3,000 newtons, we'll keep accelerating the car at that 3 meters per square second, and it'll keep getting faster and faster. If we don't, then its acceleration will drop. It responds to it. And so that then means that we can think of it in a different way. We can also think that an object with an acceleration can apply that force. So this car, now traveling with an acceleration of 3 meters per square second, if it were to smack into, let's say I'm standing on the road right here, here I am, and this car comes along with this acceleration and this mass, it's going to hit me with a force of 3,000 newtons, right? And that's not going to be very fun. And there we go, right? So think of it in two ways. The force required to accelerate something, but it's also the force that can be applied by something with that acceleration and mass as well. Cool. The next thing then is the third one. So the third one, again, pretty commonly used, is the law of opposites, right? So equal and opposite reaction forces. Newton says that for every force that you apply to something, there is an equal and opposite reaction force. So if I were to press down on the table, then the table pushes back against me. But technically, even that, I'm pushing down on the table's then pushing down on the floor, and then the floor is pushing back up, right? So everything pushes back with an equal force. It explains why if you tried to slap someone in the head or something, it's going to hurt your hand as well, right? Because as much as you're hitting them in the head, then their head is hitting your hand back as well with the same force. In the same way that tennis players get wrist injuries and that kind of thing, because if I'll do my best to draw out a tennis racket here, that'll do. Probably shouldn't have done it yellow, because now we're going to do a tennis ball. if they're hitting the tennis ball with 100 newtons of force, the tennis ball is hitting back with 100 newtons of force, which means they're experiencing 100 newtons through their wrist as well, which is why they can end up with an injury overall. It's just Newton's third law all the way through. A more interesting one though is the concept of a normal force, right? So when we're standing on the ground and our weight is pushing down, the ground is pushing back up, right? And so this is under gravity, which we're going to get to as well. But if you're pushing down with a certain amount, the ground pushes back up, and this is actually what makes us feel our like sense of weight overall, right? If you take the ground away, you no longer have that normal reaction force, which means you no longer get the sensation of your weight because nothing's responding to it in any way. So if you were to jump in the air, you don't feel your weight when you're in the air. Or if you were to free fall or something, you won't feel your weight. And we're ignoring the concepts of air resistance and everything else as well, because you don't have a fixed surface to respond back with, right? And so there's applications of that in the GAMSAT where they talk about things like a patient on a bed and you've got the two legs, which we're going to get to more later on. But if you've got a person who's, I don't know how long they should, oh God, I can't really draw a person here. There we go, a bit of a stomach on him. There we go, arms. Oh, that's not a head. There we go, that'll have to do. There we go, I'll give them some hair as well. And if they've got a certain amount of weight pushing down, then it's pushing down on the bed. The bed is then pushing down on the ground, and then the ground is pushing back up again, like that, right? And we can talk about the weight distribution based on the normal forces that are responding through each one. So there we go. So those are our three Newton's laws, and we're going to be applying those. Have those in the back of your mind every time you're doing a question. If there's forces, these will always apply every time. They never don't apply. It's just that sometimes they're not as relevant to answering that particular question, but you can always explain those three laws in any given scenario. So then the next one we have is gravity and gravitational fields. So let's just go down here, I think. So gravity and gravitational fields. So I think we're all familiar with the concept of gravity itself in terms of how we experience it, but what we want to look at is where does it come from? So first of all, let's start with gravitational fields. So a field is obviously an invisible field or area that is responding to some physical phenomena or some physical object in some way. And in the case of gravitational fields, it's the response to something that has mass, right? So technically everything with mass has its own gravitational field, really pulling towards itself. It's just that we don't experience most of them because most things don't have a large enough mass to do so. So technically this pen has its own gravitational field. The problem is its mass is so small that we're not really feeling the pull in any way, right? Because we are much heavier than it, and so are many of the objects around it. And on top of that, we're sitting on top of Earth, which weighs a whole lot more, and its gravitational field is kind of masking everything. So if we think of something with mass m, the idea is that a gravitational field will point concentrically towards the center of mass, like this. And so all these yellow arrows are going to be technically force vectors or field vectors, and they're trying to represent the direction and the kind of shape of a gravitational field. So really we only care about planets, right? We're not really going to be talking about the gravitational forces between two inanimate objects. We're going to be talking about planets and moons and that kind of thing. And so the formula for the gravitational field G is capital G times big M over R squared. They will always give you capital G. You do not have to memorize it. So it's a constant, 6.67 times 10 to the negative 11, which I always remember rhymes. And then that will go into every single calculation. M is going to be the mass of the object that the field is relative to, right? And so this here, we'll just say the mass of the planet, right? That we're talking about, whether it's Mars or Earth or this or that. And then R is going to be the distance from the center of mass at which we're measuring the field. So again, if we draw out, let's do Earth. like this. And here's the center of mass of the Earth. And we're trying to measure some distance from, actually, no, let's go with some distance right to the edge, right to the surface. So this would be our R, and in that case, literally the radius of the circle. And if we're standing on Earth like this, and we want to measure what's the strength of the field at this particular position from the center of the Earth. The radius of the Earth, which again, you'd be given in the question, so don't worry, is 6.4 by 10 to the 6 meters. Again, standard units. And the mass of the Earth, which would also be given, is 6 by 10 to the 24 kilograms, like that. So technically, just with that, we can work out the strength of the field of gravity. And so we can get 6.67 by 10 to the negative 11 multiplied by the mass, which is 6 by 10 to the 24, divided by the radius, which is 6.4 by 10 to the 6, all squared, right? Now, you may have to do a rough estimation of a calculation like this, so let's go through it without a CAS. First is I would do all the index laws, right? So let's just bundle all of the 6.67 and the 6. Let's get them together. Then let's get the 10s together. So negative 11 plus 24 is going to be positive 13. And then over here, I'm going to split this and say 6.4 squared. And here I can raise the power and get 10 to the power 12, like that. So then this 6.67 by 6 is probably pretty similar to 6.4 times 6.4. So I'm going to roughly cancel those. And then here I get 10 to the power of 13 minus 12, applying more index laws, and I get 10, right? And this is measured either in newtons per kilo, or it can be measured as 10 meters per square second as well. And there's the gravitational field strength on Earth. It's really 9.8 on Earth, because again, I've got some rounding error, but it comes from that formula. And so if we wanted to know what was the gravitational field strength at some other distance, we just go all the way from the center of Earth. We get that distance, we use that as our R, and then we plug back into the formula and we can get an estimate on the gravitational field strength at that position as well. Cool. Now you'll notice in this here that it's got two different units. So we can think of it as the force per kilo, or we can think of it as an acceleration. And that's really important, because if we go back to Newton's second law, we said that net force is equal to mass times acceleration. And if the acceleration of an object is the value of gravity, because this is the acceleration of any object, if we do the classic like drop the pen and the feather thing, ignoring air resistance, they should drop at the same rate. That is because gravity is an acceleration. Then we can work out, well, our body mass, for example, let's say someone has a weight of, or a mass of 70 kilos on Earth with an acceleration of, let's just do 10 meters per square second, we can work out their weight force that they're pushing down on the Earth with, 700 newtons. And remember that because they're pushing down with 700 newtons, it means that Earth is pushing back up with 700 newtons as well. That's that stuff there. So obviously if you were further away from an object, then the gravitational field strength weakens. So we can see there's an inverse squared relationship in the maths. This is probably one of the more important things for GAMSAT, is we can see that there's an inverse squared relationship between gravitational field strength and the distance from the center of the object itself. So if we turn that into a proportionality statement, G is proportional to 1 times 1 over r squared. G is inversely proportional to the square of distance. And so what that means is that if you were to say double the distance, let's say we did that here in this particular case, this is 2 times the radius of the Earth, we can actually predict, we can just put a 2 in for doubling r, apply the squared to it, therefore G is proportional to a quarter. So that would mean if you double the distance, you quarter the gravitational field strength. And so therefore G at this particular point is actually going to be 1/4 of what it was at this point over here, which was 10, and that gives us just 2.5 newtons per kilo, or meters per square second as well. And so what that would mean is that if you were in space at this point here, apart from the fact that you're free floating, if you were to stand on a platform under that gravitational field strength, then your weight would literally be 1/4 of its value. Keep in mind your mass in kilos still a scalar, is exactly the same, it doesn't change, but your experience of weight, which is actually a force, newtons, would be a quarter of its value. And we can also explain that as well, because if you go in something like a lift, if you go in a lift or an elevator, and when you're going upwards, for example, what's happening there is you're accelerating against gravity. So gravity's pushing down and then you're accelerating past it. And so what's happening is you're getting a summation of forces overall, because you've got the acceleration of the lift going back against you, and it kind of presses you into the floor, which means that not only are you pressing down with your weight, which say is 700 newtons, you're then also pressing down as well with the extra acceleration. So 70 kilos times the acceleration of the lift, which might be 2, so another 140. And so you end up feeling a lot heavier because now you're pushing down with 840 newtons, and again, under Newton's third law, it's pushing back with 840 newtons. So you feel heavier than what you normally do when you're standing still. And then the reverse, when you're actually going with gravity, it's taking away some of that force, right? So if you're in the lift, gravity's going down at 10, and then the lift is going down at, say, 2 again, then the net acceleration overall is actually only 8, like that. And so therefore we could do it a different calculation, 70 times 8, 560 newtons. So then you feel less than 700, so you feel lighter as well. So this is the proof that gravity is just an acceleration, and when you accelerate, you know, vertically, up or down, you're interacting with gravity, and you can change the experience of it as well. Cool. All right, let's go over this side now. So then from there, driving forces and frictional forces. Okay, so this one's pretty quick. I won't spend too much time on it. The idea behind this is just, let's say again we have a box. Driving force is something that is pushing or propelling some object. So this is going to be F drive. I'll just put FD. Friction is the resistive force that is put forward by a surface, right? And it tries to resist the movement that's being put forward by the driving force. So if we were, you know, pushing a box along a slippery floor, we might have very little resistance and maybe no frictional force at all. If you're pushing it along carpet, there's going to be a lot more friction, and therefore you're going to have some frictional force, and it's going to work against you. So here, let's say we're running it along carpet, and the driving force is 100 newtons, the frictional force is 30 newtons. It means that the box is not going to move as quickly as what we wanted it to. It's going to have a net force. I'll just do it here, a net force of 100 minus 30. And really all we're doing there again is adding up in the individual dimensions or in the individual horizontal and vertical components. So you can see that this is in the negative direction. So I'm really doing 100 plus negative 30 gives me a positive 70. And because it's positive, it tells me that it's still directed in the positive direction, because remember, forces are vectors, vectors have direction to them. And now I can work out the net force. If I wanted to, if I knew the mass of this box was say 10 kilos, I could then also work out what the acceleration of the box will be, because I can use Newton's second law and say that A is net force divided by mass. The net force was 70 newtons from up here, and the mass we said was 10 kilos. So therefore I've got 7 newtons per kilo, which we saw from gravity is equivalent to meters per square second, like that as well. Whereas if I was to raise the weight, or the mass I should say, then the acceleration will drop to respond to it, right? If it's heavier, it's not going to move as quickly. Okay, and so then there's all kinds of different types. You can have friction on wheels and that kind of thing as well. The main thing is just getting the directions right. Friction should always go in the opposite direction to the driving force. And then finally, let's finish off now on net force and equilibrium. And what I should have put in there as well is we're going to look at force diagrams to actually work these out. This is the most useful bit of this part of physics, is knowing how to do force diagrams. So when you have lots and lots of stuff acting on an object, you want to know how to actually represent it logically so that you can work your way through it. So say we have, let's see, an object like this, and it's going to be sitting on a table like this, And this object here is going to have a mass of 2 kilos, but it's going to have a bunch of forces being applied to it. And we're going to work out what's happening to it overall. So the first thing is we're always going to have the weight force, and that should come from the center of its mass. So generally speaking, the center of the object. And we're going to go straight down like that. And that's going to be equal to mass times gravity, or mass times acceleration, using Newton's second law, right? This is our weight force or gravitational force. So this would be 2 times 10. We'll just take 10 as the value of gravity on Earth. That'll be 20 newtons down, like that. Then upwards, we would have a normal force responding, right? Technically, the normal force is coming from the table. I'm going to cheat a little bit here and just go from the center of gravity, center of mass, up, and it should be equal and opposite, Newton's third law. This is our normal force, often written as Fn or just N, and that's going to be 20 newtons as well. So vertically, they're in what's called equilibrium, meaning that there's a balancing out of the forces and the net force is 0. If we then go in the horizontal component, what I'm going to do is say that something is pushing on this side with a force of 50 newtons, like that. And so I wouldn't draw it like this. I would actually draw it from here, from the center again. And we're going to put 50 newtons on that one. And then let's say there's a frictional force. Normally frictional forces are drawn from where the surface is interacting. And let's say the frictional force here is 60 newtons, right? So what that means is that the horizontal components have not balanced out, but because the frictional force is greater than the driving force, so 60 is greater than 50, it means the driving force has not applied enough force to actually get the thing to move. So it's not actually going to move left, because remember, friction is not an applied force, right? It's something that is resisting movement in some way. So we can predict that in this case, the object will sit still and it won't move despite a force being applied, right? It'd be like trying to push against a fridge or something and it not budging until you push more overall. Whereas if we were to up the force, this is pretty basic calculations, obviously, to say 100 newtons, so we double it. Now we have a net force calculation. So net force horizontal is going to be positive 100, take away the 60 frictional, and we get a net 40 newtons to the right. The net force in the vertical component is going to cancel out. We're going to have 20 newtons up, 20 newtons down, 0 newtons up or down. And so putting that together, we'll just draw it over here, that's just an arrow pointing this way with a value of 40 newtons. So that would mean that the box should slide to the right, like that. And again, we can work out what its acceleration is, right? Because mass times acceleration is net force. And we know the net force is 40, so we can get acceleration is net force divided by mass. So therefore 40 divided by 2, and that would have, well, that's big. That would have 20 meters per square second acceleration, like that. Okay, so what we'll do now is we'll go through some more questions in kind of GAMSAT kind of context to apply all of this, right? So let's first go through the concept of apparent weight and normal forces. So we can take, for example, the classic example of the patient on the bed, right? And then we'll just draw, oh, again, can't really get the head right. There we go. They're lying on the bed. There we go. Let's say that this time their mass is going to be 90 kilograms. And they tell us this is leg A, this is leg B, and the distance between leg A and leg B is, let's see, 2 meters, right? But what we also know is that their center of mass is not in the middle of their body, right? Which makes a lot of sense. We're actually kind of top heavy. So let's say their center of mass, we'll call that XM, is going to be roughly, let's say they're exactly 2 meters tall. It's a very tall person. Ignore that it's not drawn perfectly to scale. Let's say they're 2 meters tall, so literally the ends of their body are right on the legs of the bed itself. And their center of mass is going to be here, which is going to fall around about 1.7 meters above the ground when they're standing normally, right? So that would mean that if we break that down, this here is 1.7 meters from their feet, and then this is 30 centimeters here, which now that I think about it is tiny. They have a tiny little head, but anyway, that doesn't matter. I'm trying to get that right. Yeah, it's probably a little bit high, but anyway. So from there, we've got their mass. We're going to work out how much force is applied through each of the legs of the bed, right? The goal is, because the bed is assumed to be not moving, then it means that the bed is in equilibrium. What that means is that all of the upwards and downwards forces and all the left and right forces, if there are any, are all cancelling each other out. So the net force is 0, and that would be equilibrium. So in order to do that, though, we have to think, well, it's not going to just be an equal distribution of weight through each of them, right? Simple way to tell is if I was to take my hand and then press more with the heel of my hand than my fingers, but I'm pressing all of it, I can't just divide the force evenly by 2 and say, well, half the force is felt down here and half the force is felt here. I have to actually take into account where the weight distribution is going to be, or where the force distribution is going to be. So if I'm pressing more on this side down here, there's going to be more force experienced through that section. So the way that we do that is we chop it right here. Well, we don't chop the person, but we chop through the diagram here, and we look at the relative fractions of distance to each of the legs from the center of mass. So here, this one's 0.3, this one's 1.7. To make that a little bit easier, let's call that 3, and then this one here 17, so that we can compare them as ratios, right? And then the total thing would be 20. So for leg A, that is 17 units out of 20 away from the center of mass. And then this one over here, to B, this is 3 away. What happens is it kind of crosses over. So that means that 17/20ths of the weight is actually going to push to B, and 3/20ths is going to push this way, right? Because it's further away. And if you think about it, where the center of mass is closer, you're going to have more force pushing through there. If you had all of it directly over this, well, then it would push all through B, right? So that means that if we want to work out the force through here, the force is just going to be whatever their weight force is. Let's get their weight force actually. So their weight, which is also Fg, doesn't really matter about your notation because it's a multi-choice exam, is again going to be mass times gravity. So that'll be 90 times 10, which will be 900 newtons. The fraction of it that goes through B is going to be 17/20ths. So 17/20ths of 900, like that. B, it's going to get, sorry, A, it's going to get 3/20ths, the leftovers of 900. Now really, because they're the leftovers, you could just work with the easier one. That one's messy, so I'm just going to go with 3/20ths over here, but I'm just going to clean that up so it looks a little bit nicer. And that, then I can cancel off a couple of zeros, and then I can do 3 times 9, which is 27, add the 0 on, so it's 270 over 2, and then I can halve that there as well and get 135 newtons. Must be going through this one. Over here, this would just be the leftovers. So rather than doing this now, I know it's just 900 take away 135, like that, which will give me 765 newtons experienced through leg B. And there we go. What they could also do though, is they could give you not the actual length or the distance between the two objects. They could tell you all of it in proportion of the lengths instead. So we could have the two legs, so A and B, but this time we just have some length between them, which we'll call, or some distance, which we'll call D, and they're saying that the center of mass sits here. I'll leave the person's body out this time, and that happens to be, we'll say 3/4 of the distance, right? And then that means that over here we have 1/4 of the distance left that way. So then if they have a mass of, let's stick with the 90, so therefore their weight is 90 times 10, so 900 newtons. Then now I know that even without the actual distance itself, I can still work through it. I can go, well, the force here at B is going to be the flip side. It's going to be 3/4, right? Just the fraction. 3/4 of the weight will push through there. Whereas over here, this will just get 1/4 of the weight that'll push through there, right? And so this will give me 225, and this will give me the remainder, right? You can see I'm going for the easier one again each time. So then this will give me 600 and 75 newtons and newtons, and I've solved it again, like that. You can also do it by proportion. So if they didn't give you the mass, then you would just know that the force would be 3/4 times their weight, which was mass times 10. And you can kind of simplify that and get 30 over 4m. And you can start creating equations as well, right? So this is what I mean by kind of predicting or anticipating questions, is think about different ways you can play around with it, try to use variables instead of actual values, and play around with the algebra a little bit as well. A really good application of gravitational fields would be one that doesn't involve many numbers, and this is where you want to really think about the principles behind the maths and behind the explanations for the maths itself. That will actually serve you a whole lot better. So if we come back to, and they'll give you this in the question, if we know that this is the gravitational field strength, right, and then we know that they can kind of push and pull on each other. Let's say we have two objects and they tell you that there's two planets. I might actually make sure that that actually comes out a circle. So let's say we have one here and then a slightly smaller one over here, and they have different masses. So let's say this one has a mass of MA, so there's going to be no numbers here, and this one's going to be a mass of MB, right? Let's say though that this one here is half of MA, like that, so it's MA on 2. And we know that the radius of this particular one is R, and this one over here is going to be, we'll call it K. There's no mathematical relationship between them. And then we have a distance between them as well of, let's see, we'll do 10 to the power of 6 meters, like that. And then what we're going to look at is where could, say, an astronaut sit so that they're experiencing zero net force or zero gravitational field. So it means that we're trying to find, if they've got gravitational fields, if we kind of draw these in, this one's pulling in like this, and then this one over here would be pulling in, and we're trying to work out where do they cancel each other out. So these two here, where do they actually cancel each other out to zero? So what we can do is, first of all, we know that it's going to cancel out further away from the bigger one. This is where you can start using the reasoning, right? The heavier one is going to have a bigger pull on it, right? So where the little one, MB, is going to be able to cancel it out, is probably going to have to be closer to where B is, where its force is stronger, so that it can start to work with or cancel out or be equal to the gravitational field strength of the heavier one. You're going to have to move a lot further away from the heavy one to get the same kind of field strength as you would get from a lighter planet. So I'm going to predict that that point sits closer to this, to B, than to A, but it doesn't really matter where I draw it. And so then what this becomes is, let's say as well, they'd probably give you this in the question, it occurs at some altitude. Remember, altitude is from the surface. It's going to occur at some altitude of A, like that. Immediately now, I'll switch colors. This is how I'd work this through. I'd go, all right, well, this here is 10 to the 6 minus A, that distance there. And I can now work out my relative radius from the center of mass of each here. So this one, my R is actually going to be, I'll call it R1, is going to be this R, the radius of the object, plus 10 to the 6 minus A. And then this one over here, which I'll call R2, is going to be K plus A, like that. And now I can create little equations. So what I want to do is I want to say that G1 is equal to G2. But how do I get G1? I go, well, that's Gm on R squared. So G is a constant. I'm just going to leave that as G right now. The mass, which is Ma, and then over the radius, which is R plus 10 to the 6 minus A, all squared. And that, I want it to be equal to the G calculation of the second planet. And that one there is going to be G times the mass of planet B, but I'm going to immediately put it in terms of A, like that. So Ma on 2 over, and its radius, which is K plus A, all squared. Now we've got them equal. And now I can pretty much just rearrange and solve that from anywhere. So it's more of a maths thing, but it uses the reasoning of the inverse squared relationship between gravitational field strength and distance. We know to predict that it's going to sit closer to B overall, right? So, and we can use that to kind of confirm our working as we go through. So let's say then that it said, let's say it said solve MA in terms of the other variables, right? So in terms of A, R, and K, like that. And it didn't say G. The reason why G is not going to be in there is because mathematically we can cancel that. So we can cancel it right here. We can just divide it across and it would cancel. So we end up with MA over R plus 10 to the 6 minus A all squared is equal to MA over, and then here I can put the 2 down. So K plus A squared. And what that also means is that now the MAs are gone, which means that these two are equal, which means I could create some other relationship. So therefore R plus 10 to the 6 minus A all squared is equal to 2 times K plus A all squared. And I can start solving something from there as well. So let's say I wanted to solve for K or something, then I could just go, well, R plus 10 to the 6 minus A all squared divided by 2. I could then square root that as well, right? And then I could minus the, when I solve for K, so I can minus the A across as well, like that. And there we go, now I've got K. I could obviously solve for anything else as well, but it allows you to think about how the rules work, and then you can just play around with the algebra from there. And it becomes less of a physics question if you notice. It becomes more of an opportunity for algebra. So this is where, when we go through these things, this is not, they're gonna ask this question, you need to be able to follow this exact question. It's very, very unlikely. More so it's getting familiar with how to manipulate the formulas and some of the proportionalities between them so that you can adapt to any given question as well. All right, so that's pretty much everything that I wanted to get through in this one. It's obviously bite-sized lessons each time. I'll go through more in detail as we go through each of them. The next one will be getting into more like kinematics, graph analysis, and that kind of thing. But we'll also work through electric circuits, and what else, magnetics and that kind of thing comes up a little bit in it, not a huge amount. And then some radiation physics as well, which does come up a little bit throughout. So on top of that, I'll probably start on chemistry as well. I know OChem is pretty important, but because some people have no science background, I'll probably be starting with the concepts of moles and stoichiometry to get us started. And then we'll pretty quickly try to progress into the organic chemistry stuff to get that out of the way, because we all know that's the majority of what comes up in the GAMSAT as well. Cool. All right, I've also put together a resources page, so if you haven't already checked it out, then I'll leave a link. Check that out there. I'll probably be adding more science-based questions for section 3 to it, as well as worked solutions. So yeah, keep a check on that. But otherwise, I'll try to have these videos out pretty frequently, hopefully a couple a week if I can muster it. Just depends, because it's a pretty busy time with all my school students as well. They're all heading into their exam season pretty soon, and it's a pretty busy part of the year, but I'm just trying to knock these out in between. Lockdown definitely helps, so I'll do that as well. All right, I'll see you in the next one.